Hi everyone, my name is Azer Aliyev, Baku Higher Oil School 3rd year Process Automation Engineering student, and today we're gonna talk about 2-bit synchronous counters with state decoding. And what's counter? Counter is simply a device that counts how many times any particular event has happened. And there are two types of counters, which are synchronous and asynchronous counters. The main difference between them is that in synchronous counters, the flip-flops are fed from the same clock source, rather than one having the output of the other. So we will use D flip-flops for this purpose, and here you can see the truth table of the D flip-flop. When the clock signal is 0 or low, flip-flop holds the output. I mean, if it was Q and Q inverse previously, it will stay like that when the clock signal is 0. But when the clock signal is 1, the output of Q depends on the input D. That's to say, if D is 0, Q will be 0 and Q inverse will be 1, and if D is 1, Q will be 1 and Q inverse will be 0. So we said that in order to construct the synchronous counter, we have to feed all the clock inputs from the same clock source. Let's do that. But how to connect these other inputs and outputs? So we will have to construct a truth table for that, and we will use corner map method to get the proper logic expressions. So let's do this. But firstly, we have to construct our state diagram. So we aim to design 2-bit synchronous up counter. So let's draw our state diagram. So our state diagram will look like that. The output has to be first 0, 0, then it goes to 0, 1, then 1, 0, and then 1, 1, and it returns to 0, 0 state. So due to our state diagram, we construct a new table. These two columns represent the current state, these two the next state, and these two is the required input. So Q0 is here represents the LSB, the least significant bit, and Q1 represents the MSB, most significant bit. So as we said in the state diagram, we have to go from 0, 0 to 0, 1 to 1, 0 to 1, 1. If our current state is 0, 0, we want to go to the 0, 1 state. And we fill all these parts like this, as 0 from 0, 1 to 1, 0, from 1, 0 to 1, 1, and from 1, 1 to return to the 0, 0 state. And we said earlier that the output of Q depends on the input D if the clock signal is 1. So to get 0 in Q1, we have to give 0 to D1. And like that, we fill these parts, and then we will get the logic expressions using corner map method. These are the tables that we will use for corner map to get the logical expressions. So from the table above, we will get the logic expression for D1, and from the table below, we will get the logic expression for D0 input. So we said that, for example, from this current state, in order to get this next state, we have to give these inputs to the D1 and D0. So we will fill these tables using that table. And let's do this. Logical expression will be in the form of sum of products. So we have to find the 1 states from this table. So the first table, let's do this firstly for the D1, and we see that from this table we see that when D1 is 1, when Q1 is 0, and Q0 is 1, and Q1 is 1, and Q0 is 0. So we put these values to this on this table. When Q1 is 0 and Q0 is 1, D1 has to be 1. And when Q1 is 1 and Q0 is 0, D1 has to be 1. So then we group this alone and this alone, and we get logical expression of y is equal to Q0 inverse Q1 plus, and I mean or Q1 inverse Q0. And we know that this is the expression of XOR gate. So it will be like that. And we do the same thing for the D0, and we see that D0 is 1 when Q1 is 0, Q0 is 0, and when Q1 is 1, Q0 is 0. Q1 is 1, Q0 is 0. So we put these values on this table. Q1 is 0, Q0 is 0, D0 is 1, and Q1 is 1, Q0 is 0, D0 is 1. So we group these two together, and we get the logical expression of Q0 inverse. So we will use these two logical expressions to connect these pins on our D flip-flops. So we got that. We said that Q0 is the LSB. This D flip-flop represents the LSB, and this flip-flop represents the MSB. So we've done everything, and it's time to construct this circuit on the breadboard. That's the construction of the circuit for 2-bit synchronous counter with state decoding. This is 555 timer. This is 555 timer that I used to give clock impulse to the D flip-flops, and this is D flip-flop. It's dual D flip-flop, and I mean there are two flip-flops, D flip-flops inside this element, and that's the XOR gate, that's the NAND gate, and that's the buzzer. NAND gate and buzzer are used for the state decoding part. I will talk about that later. These two LEDs is used as an indication of the states. So I tried to decode the 1-1 state. As you know, decoding is converting binary number to its decimal value or vice versa, and I used buzzer for state decoding and I decoded the 1-1 state. So when the 1-1 state is reached, I supply the output of D flip-flops to the NAND gate. I didn't have AND gate, and I constructed it from NAND gates, and that's quad 2-input NAND gate, and that means there are 4 NAND gates inside this element. And when 1-1 state is reached, the first NAND gate will give the output of 0, and I supply this output to the input of the second NAND gate, and second NAND gate here simply plays the role of inverter. So it will give output of 1, and buzzer will give us a signal at 1-1 state. So here you can see that our circuit is working, and this LED is used to see when the clock signal is supplied to the flip-flop. So let's see, it's 0 0, it goes to 0 1, then 1 0, and 1 1. So, and that's what we wanted.